Hello everybody, this will be the first Physics Friday video. My name is Erick Quintana, and today we are going to talk about perpetual machines. So I saw recently a post asking a question on the internet about why in the scenario that I'm drawing right now, why the scenario would not lead to perpetual motion. So here we have a van or a car of some kind, and on the other hand, we have a magnet. Now, the magnet should be creating a force on the van, moving it this way. However, if we actually do this in real life, it turns out that overall, the van should have no change in velocity. That's interesting. What's happening here? Well, I am a physicist at heart. So you know what? This is a magnet. This is a big old truck. There's like mass. I don't know. This probably has mass. You know what? What I'm going to do is I'm actually going to just simplify things. I'm going to say there's one ball connected to a rod. And I'm going to say that the rod is massless. And, you know, there's another ball here. And what happens is that this ball causes a force on this ball. All right, and now I'm not going to specify exactly what type of force it is. So, you know, let's just ignore the fact that it's magnetic in the original case. All right, so we have a ball, and, you know, this simplification probably didn't elucidate anything because we still have a case where one ball is experiencing a force in the opposite direction. But I want to actually redraw this a bit. And this is not the same scenario, but it is similar. If I were to bring you this scenario, and I told you that there was let's say in this case there's a ball on one side and there's another ball, and this ball is causing a force on this ball. And I asked somebody off the street, would this ball move towards the other ball? And, 9 times out of 10, people would probably say that no, this ball would not move because this block is in the way, right? But what's different about this and this? That makes some people question as to why this ball is not moving forward. Well, it's probably because the block is separated from some distance. Now, the explanation for this, it actually goes back to Newton's, is it second law? I always forget. It's for every action or for every force, there is an opposite and equal force. So the explanation for why this does not move forward is that actually when this ball exerts a force on this ball, there's an equal and opposite force I'm just going to label these being exerted. And because they're equal and opposite, if you added up the two forces, you would end up with 0 net force. And that should explain anything. So that wasn't too much work. 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 Wait a second. Did this really explain the original scenario? Because the fact that I didn't talk about what was specifically causing these forces, well, there's a lot in the nature of the force that's important. Because in this case, it's a magnet. Now, what's interesting is that magnetic forces do not obey Newton's third or second law. uh, I can show you an example for this. So the force, first off, let's just define what the force of a magnet is, or magnetic forces. So the magnetic force is given by a charge, a velocity on a particle. So if a particle has some velocity, and the direction of the magnetic field. So let's say that there's a magnetic field pointing up. This right here is the cross product. Basically, to find, this is not the same thing as just multiplying or taking the dot product. Basically, it has the property that the magnitude of the force is equal to the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field multiplied by the sine of the angle between them. And the direction is just given by the right-hand rule. So in this case, if there is a charge with, let's say it's positive, moving to the right and the magnetic field is pointing up, I'm just making sure I get this right. So QV cross B would actually point out of the page. And the charge would actually go in and out of this place if it was under the action of this magnetic field. Now, the thing that's interesting about this is that if we look at, let's say there's a positive charge moving to the right, and then there was a negative charge moving up. Now, one thing that I forgot to mention is that the way that the magnetic field works, the magnetic field created by a charge is proportional. Magnetic field is proportional to QV cross R hat, which in this case is just kind of like in the direction of from one charge to the other. So in the case of the positive charge, I'm going to use a green color for the magnetic field. The magnetic field of the proton at the position of the negative charge, well, if you look at the if you look at the R hat actually points in the same direction as the velocity vector. So the angle between them is 0 and sine of 0 is 0. So at the position of the negative charge, the magnetic field is equal to 0 due to the positive charge. But in the case of the magnetic field at the position of the positive charge, well, V points up and R hat points to the negative left, to the left direction. The angle here is 90, sine of 90 is 1. So the magnetic field has a direction actually pointing up. This means that there is no force on the negative charge due to the magnetic field, but there is a force on the positive charge due to the negative charge. And that violates Newton's law. Now, we know about this. Physics has known about this for, I think, ever since electrodynamics has been known about. And they've actually come up with some explanations that are a bit above, like maybe they focus on the momentum of the fields. And it turns out that in that case, Newton's law still works. However, if you notice, these are actually just point particles, or we can assume that they're point particles. The magnet actually works a bit differently. So a magnet, in this case, a horseshoe magnet, has a north side and a south side. And the magnetic field, I said I was going to use green, points from the north side and goes to the south side. And it kind of does this all throughout the magnet. And what ends up happening is that this magnetic field, in the case of because the truck or the van was made out of metal, the magnetic field goes through and actually aligns the magnetic moments of the metal. And what causes is that this actually causes this to be polarized. So if the north side is this way, then there's a bunch of little atoms, and they're underneath the presence of a magnetic field, and they all align to the magnetic field. And what ends up happening is that a magnet, you can think of it as a magnet, is created. This will actually create a force this way, and because this is now creating its own magnetic field, which I'll use with a lighter green. So this is now causing its own magnetic field. So this now has a force due to the magnet that was induced in the truck. So in this case, the Newton's law still explains it, but you kind of had to think about what exactly magnetic forces do, what exactly the magnetic force is, before it could be explained further. Now, there are a few things that I'm kind of glossing over. One of them probably is that you've probably heard that magnets do no work. So why is there kind of a force being created? I'll leave that for the viewer to as homework for the viewer. All right, so thank you, everybody.